Hi class! In the previous section, we used matrices to help us solve systems of equations. We learned about row operations and writing matrices in reduced row echelon form so that we could find the solutions to our systems easily. However, that was our first time looking at matrices, and these matrices are something that can be explored as an individual algebraic element itself. That is, we can learn how to add two matrices together or subtract them. We can learn how to multiply them in terms of scalar multiples, and next section we'll learn how to actually multiply a matrix by another matrix. And so these properties of matrices are what we're going to be exploring today in section 11.4. The first thing we want to do is define what a matrix is. And a matrix is an array of elements that is arranged into rows and columns. Now we want to call the order of our matrix m by n, always doing our rows first and then our columns next. And if we have an m by n matrix, then it would be represented by elements. If we call the matrix capital A, then all the elements would be lowercase a, but they would have two subindices. We call them Aij, where the I tells us which row we're in, and the J tells us which column we're in. So this element right here would be in the second row, first column, while this element over here is in the first row, nth column. And this element would be in the mth row, second column. We use the lowercase a to signify the generic element in capital A matrix, and likewise we would use lowercase b for a matrix capital B, and lowercase c for elements in matrix capital C. And so we would name the elements after the name of the matrix. Let's check your understanding of this right now. In this 3x4 matrix that you have labeled matrix B, I've asked what is element B in the second row and third column, and what is element B in the third row, second column, and what position is -3. Do you think you could get all three questions correct? The first one says second row, third column, and so that would be -4. The next question says third row, second column, so that would be the 6. And the last one says what position is -3? The -3 is in the third row and the first column. So we would say that would be the element in the third row, first column. Now that we understand how the naming of the elements goes, we see this definition at the bottom of our page. It says that matrices A and B are equal, written that A is equal to B, if they have the same order, or rather if their dimensions are the same, and their corresponding entries are equal, meaning that each element in the same spot is going to be equal to each other. That is, matrix A is equal to matrix B if and only if each element Aij is equal to each element Bij for all I and j that are applicable for each matrix. Given the definition, we know that the first matrix can only be equal to the second matrix if and only if each element in the corresponding spots are equal to each other. That means that if my x is in the first row, first column, then it has to be equal to this 5, which is also in the first row, first column. Likewise, this x plus y, which is in the third row, second column, must be equal to this element here, which is in the third row, second column. Once we make that statement, then it's very easy to solve by substituting the value of x into that second equation, and we get y is equal to 4. So we've solved for the value of both variables that are in this question. In order to add matrices or subtract them, they have to be the same order. That is, they have to have the same amount of elements in each row and each column. That way you can add the corresponding elements. So if we want to ask ourselves E plus F, you're just going to take each element of E and add it to each element of F in its corresponding spot. you can see that I wrote E plus F to be the sum of the elements in each location. So you can see 2 plus negative 3 is the sum of the 2 here and the negative 3 here, as they correspond to each other. And the 4 plus the negative 5 is the 4 plus the negative 5 in the corresponding spots. We can simplify this to be E plus F is equal to, and then you want to simplify each one. So 2 plus negative 3 is negative 1, 7 plus 9 is 16, 10 plus 1 is 11, negative 1 plus 12 is also 11, 4 plus negative 5 is negative 1, and 8 plus 2 is 10. You have to be careful because we're adding positive and negative numbers, so sometimes you might actually be subtracting. So make sure that you just double check your work the whole way through. Now at the bottom of this question I do ask, what would you get if you added F plus E? Would it be the same or would it be different from this matrix that we just found? Well, if I took F plus E, what I would say is negative 3 plus 2. And you would still get that negative 1. And so F plus E is going to be all the same components of E plus F, just when you add them together, they are still commutative. So matrix addition is also commutative. So F plus E would be the same thing as E plus F. You have to be very extra careful when you're doing subtraction, because when we subtract negatives, it turns into a positive. So I'm going to go ahead and write it very slowly as each element subtracting each other element. And when I get to a negative, I have to write parentheses. So there'll be 4 minus parentheses negative 5. That will help me. And then when you rewrite it, you want to turn all of those into addition. So that turns into 2 plus 3. And let's just keep this without simplifying it one step. We're just going to change the minusing a negative into positives, or into addition. Okay, now let's go ahead and simplify each of these. We change that to addition, so that's easy. 2 plus 3 is 5. 7 minus 9 is negative 2. 10 minus 1 is positive 9. But negative 1 minus 12, because those are both negative, we add their values and we keep the sign. So that becomes negative 13. The 4 plus the 5 becomes a positive 9, and the 8 minus the 2 becomes a 6. And make sure to use the matrix brackets around your matrix each time. And I just want to point out real quick that we had some very special things going on with the first element, the element under it, and the one to the right. And you have a positive minus a negative, that turns into addition, that turns into a positive 5. But when you had a negative minus a positive, that turned into addition, but it became negative 13. And those are two different values that we get. A positive 5 was positive, while the negative 13 is negative, and that just depends on where that negative sign is and how you're adding them and combining them. So be extra careful when you're doing subtraction. The next question asks us to find matrix J minus K. And when we look at matrix J, it is a 2 by 3 matrix. When we look at matrix K, it's a 2 by 2 matrix. So you might be asking yourselves, well, do we just subtract the first 2 columns and then write the last column? Or how do we do this? They're not the same size. Well, when they're not the same order, you cannot do matrix addition or subtraction on them. So something like this is not defined. We have no way of adding or subtracting matrix J and K from each other because they're not the same dimensions. And so since they do not have the same order, then we cannot define it. Matrix addition is commutative and it's also associative. So we can rewrite this in any order. We don't have to do P plus Q plus R. We could do Q plus R plus P or R plus P plus Q. And we can group it in whichever order we want. So let's just do Q plus R plus P. So I'm just showing my work. You don't have to do this. You could add them in your head if you wanted to. So then you add the resulting matrix to each other. And once again showing my work, the result would be 10, 16, 9, and 17. And that would be my final answer. The additive inverse of matrix T is found by taking the additive inverse of each of its elements. That is, we would have -4, +1, -3, and -7. That's the additive inverse. What happens when you add a matrix to its additive inverse? That is, what happens when you add numbers to their opposites? Well, when we add each of those components, the numbers and their opposites will cancel out to make 0. We end up with just a 0 matrix. With the same order as the original matrix. That is, this is a 2 by 2. There's actually several different kinds of matrix multiplication. The first kind that we want to go over is the kind that we think about when we think about regular multiplication. In regular math, if I asked you what's 5 plus 5 plus 5, another shorthand way to write that would be what's 3 times 5. In this case, repeated addition can be written as multiplication. If we want to talk about multiplying matrices this way, we're going to say that the 4 in front of the b tells us that we're going to add b to itself 4 times. And instead of adding it 4 times, we can shorthand and by say 4 times b. We call this the scalar multiple, and it happens just by taking all the elements and multiplying it by the 4. So 4 times matrix B would be 4 times 9, 4 times 3, 4 times -1, 4 times 2, 4 times -6, and 4 times 4. The result is 36, 12, -4, 8, -24, and 16. So this would be our matrix 4b. What would we get if we multiply this matrix B by -1? Well, you multiply all of the elements by -1, and you end up getting just the additive inverse. The 4 and the -1 are what we call the scalar multipliers, or just the scalars. They tell us what number to multiply the matrix by. It's important to recognize that matrices are objects that we've never dealt with before. And therefore, when we first learn how to deal with them, we have to learn which properties apply to them. Since we talk about the matrices as an array of elements, and the elements get treated individually, and those elements are real numbers, then a lot of properties of real numbers can actually be applied to matrices. For instance, adding matrix A plus B is the same thing as B plus A. That is what we call the commutative property of addition. Then if you say A plus parentheses B plus C is the same as parentheses A plus B plus C, then that's the associative property of addition. Then if you have two scalar multiples, k and l, you could either multiply k times l first, or multiply l times the matrix A, or rewrite them so that it's k times the matrix A first, or the other way around. This means that you can associate the scalar multiples in any way you want. You can multiply them in any way you want. So this is associative of scalar multiplication. Remember that there's multiple ways of multiplying. We only know this way so far. And then we have two types of distributive properties. The first one is if you have two matrices being added and then multiplied by a scalar multiple, you could multiply that scalar multiple by each one individually before you add them. Or if you have two scalar multiples, you could add them together before you multiply by the matrix, or you can multiply them by the matrix individually. Either way, this is a distributive property. The last two properties that we're going to talk about is the zero property, which is also known as the additive identity property. This means that if you add a zero matrix to another matrix, you'll get that same matrix out in return. Additive identity meaning the same thing happens at the end as what you started off with, so it's the same thing. That's identity. And then there's such a thing as an additive inverse, and that if you add a number to its inverse, or if you add a matrix to its inverse, then you will get the additive identity as a result. Remember, the identity property is the zero matrix existing. So since there's a zero, then we call that zero the additive identity. And then the inverse is when you add two matrices together to get that zero as a result. Question number 7 asks us to multiply 2 times the sum of 3a minus b. Let's substitute the values of matrix A and matrix B into this so we can simplify. After substituting it in, we realize that we need to take the 3 as a scalar multiple times matrix A, and also I want to distribute that minus sign to all of B. So let's go ahead and do that step. And then let's go ahead and add these matrices before we multiply by the 2. Now technically the distributive property says we could multiply the 2 by each of them, but I find it easier to add the matrices first. Notice that I don't need the parentheses anymore because I only have one matrix, so you can just put the 2 outside the matrix as a scalar multiple. And then multiplying all those pieces out, and that's my end result of a matrix. Notice that this is only one way that I could have done it. I could have also multiplied the 2 first. For instance, I could have multiplied the 2 to get 6a minus 2b, and then worked on each of those scalar multiples first before adding or subtracting the matrices. But either way, you will get this as your end result, and so that's our final answer. In video example 8, we're given an equation and we're asked to solve for c given the matrices A and B. And when we're asked to do that, we could substitute the matrices in right at the beginning, but I find it easiest to go ahead and solve for c first using just our variables a, b, and c, and then at the very end, once you have c isolated, then you can solve for what it is. So the first thing I'm going to do here is divide both sides by 2. And I'm left with a plus 2c is equal to 6b. And then I'm going to subtract a from both sides. And then I end up with 2c is equal to 6b minus a. And then I'm going to divide everything by 2. And I end up with c is equal to 3b minus 1/2 a. And so if I replace my b and my a with my matrices, now I'm ready to solve. In the interest of space, I went ahead and erased what I did and moved my equation over. Now I have the c isolated, and then I'm going to replace b and a in the matrices. And then multiply by the scalar multiples. And then we notice that we have some fractions, so just take care when you're subtracting to do that correctly. Now I turned all of my fractions into improper fractions. You don't have to. You could leave them as decimals or as mixed fractions, but I find it easiest to think of them as an improper fraction like 17 over 2 than to think of it as 8 1/2. So I prefer that notation, and it's easier to think of that as one unit of numbers. For example 9, we have the story of Professor Smith who tracks his students' success by using matrices. The first row represents seniors, while the second row represents juniors. The first column is who passes, the next column is who fails, and the next column is withdrawals. We're given his fall semester success matrix and also his spring semester matrix, and we're asked to add both of these matrices together to find A plus B. So we just substitute in matrix A and matrix B and add them up component-wise. So we would get 36, 8, 6, 23, 10, and 3. The second half of this question asks us to interpret what this entry is. So first let's find that entry. We go to the A plus B matrix and we go to the second row, first column. So that's the 23. And we ask ourselves, what does the second row, first column represent? Let's look back at our first matrix here. Our second row tells us that we're looking at the juniors, and our first column tells us that we're looking at how many passed. So this would mean that there's 23 juniors who passed during fall and spring semester total. Remember that we know the 23 is from that spot. We know it's juniors because it came from the second row. And we know it's passed because that came from the first column. And then fall and spring combined because A plus B was adding up the numbers from fall and spring. So every time you're asked to do a word problem, you have to know what the units are. You have to understand and be able to interpret the pieces of your answer. It would do us no good to add up this matrix and say, oh, here's our matrix, and then not be able to read it. So you want to make sure that you understand where all the pieces are. For this last video example, we have a store called La Boutique, and we have 3 employees, Terry, Lisa, and Janet. And they had a combined sales of $7,350 in clothes and $3,260 in accessories. Now they all worked a different amount of days, and they all sold a different average of clothes and accessories per day. So I put down sort of a format. I put down a format that we're going to use to build all of our matrices. And it's important that we're doing something like this, that we use the same format for each matrix that we build, so that way each row and each column always stands for the same thing. And so I'm going to list these matrices. We have the T matrix. T will stand for Terry, and she had $550 in clothes and $275 in accessories sales every day. And then we had L for Lisa. She sold $270 in clothes. She sold $720 in clothes and $195 in accessories per day. Then we have Janet, and we don't know what her sales are, but we know that combined, and I'm going to use C for combined, that they had $7,350 in clothes and $3,260 in accessories each day. And then let's set up an equation that works with the sentence that we've given. We know that they had a combined sales, and we know how many days per week they worked. So let's set that up. If Terry works for 5 days, then she'll have 5 times the amount of her daily sales. And Lisa worked for 3 days. And then Janet worked for 4 days. Then they will end up with a total combined. And let's solve this for J and then plug the values in for the matrices to find it out. First of all, isolating the J. And then dividing by 4. We get 1/4 times this whole phrase. And then let's plug in our matrices. Now that we solved for that matrix, we just have to put that as our answer and make sure we answer the question in words. So we know that $610 is how many clothes she sold every day, and $325 is how much accessories she sold each day. Let's write that out in words. Remember that all word problems should always be written with our answer in words, answering the question as it's asked. And since it asked us to find her average daily sales of clothes and accessories, we want to address that in our answer. Thank you for this whole section. I hope you enjoyed it and that you're able to learn something from it and that you're able to do it on your own as you apply matrices to your real-world problems. Thank you and have a good day.